Good afternoon and welcome to the DSP Widgets Lab and the second part in the series of how to be a rocket scientist. Today we're going to cover something that we covered in the first lecture, or that we talked about in the first lecture, and that is the relationship between energy and velocity. That is to say that the energy in an object is equal to 1/2 mv squared. And you may recall that if you watched the video that I said something about how that could easily be derived. And today, since there was some comments on this, we're going to delve into that a little bit. So thank you for your attention, and without further ado, we'll delve into that item. Okay, so let's start our analysis. Really, to understand this whole thing, first thing we need to know, or sort of take for granted, is back in this work energy thing, that the energy that it takes to move an object is equal to the work done on the object is equal to the force the object resists times the distance we had to move it. Now, we're not worrying about vectors, so we're keeping everything simple and assuming the forces are aligned with the direction of motion, etc., so that we don't have to worry about a lot of vector calculus. But this is the simple relationship. And we're also going to apply one more fact in a more mathematical way that we are used to every day, and that's that the distance that we travel is equal to the speed or velocity that we travel times the time that we go at that speed. Now that's for a constant velocity. For a constant acceleration, the velocity that we're going at any one moment in time is equal to the acceleration times the time from 0 to t, assuming a constant acceleration. And that gives us some various relationships that are pretty basic to derive using the most elementary introductory calculus, and that is that the distance for a constant acceleration is equal to 1/2 at squared. Why? Because the velocity at the endpoint is at, but that wasn't the velocity during the whole time. The velocity during the whole time is the average of 0 and this, which is simply 1/2 at. So that gives us the average velocity times the time, which gives us the distance. So that's for constant acceleration. So we're going to do a little test case where we're going to assume we're going to move an object from a velocity of 0 at time t equals 0 to velocity v at time t. So an object starts out still, and we use a constant acceleration and get it up to speed v. Well, how much work do we do on that object, which would tell us how much energy is expended in that object, which, neglecting friction heat and other forms of dissipational energy, if we're talking about an object moving free in space, we're really talking about how much energy now is converted from work done on the object to kinetic energy, or energy of motion. And it tells us why. What we're trying to get at is, why is the total energy of an object moving through space 1/2 mv squared? Well, if we took that object at speed 0 and accelerated up to any speed v during the process, we would see that the distance that we moved during a small delta t, so we're going to say a small amount of time, and we're going to assume that it's going to add a reasonable constant velocity over that very small amount of time. So this is the distance, v times delta t. Very simple. And the force, so we got this part, so the force part would be equal to ma, and m is constant and a is constant. And remember, we chose as our test case to have constant acceleration. So we can integrate from time 0 to time t to find out the energy in this object. Well, the integral constant isn't the same here, but we can do some magic to make that the same. So remember, in constant acceleration, we said that the velocity at any one point in time, starting from 0, is the time at that point times the acceleration. So we can say that this equals ma, integrate from 0 to t, and I'm going to replace this delta t symbol with just the dt here, and now the v gets replaced with a times t. Well, again, a is a constant, so we can move it out, and what we get is ma squared integral from 0 to t of t dt. Well, that's ma squared times t squared over 2, that's doing the integral on this object evaluated from 0 to t. Well, that, the 0 comes in here and goes away. So what we're left with is ma squared t squared over 2. Okay, well, turns out that's not so bad, but what we want is this. But we observe that there is a relationship to be had between velocity and time. And again, that's this relationship. So we can say that if v equals at in a constant acceleration, then a equals v over t. And therefore a squared is going to equal v squared over t squared. So we can substitute that back in and say m v squared t squared t squared. And we can see right away these drop out, and we're equal now to 1/2 m v squared. And that little thought experiment of taking an object at constant acceleration in space and pushing it with a force until it accelerates linearly up to the velocity v, we can see that we put energy of 1/2 mv squared, and that's really all there is to it. And it's why the energy of a moving object in space is 1/2 mv squared. Okay, so that wasn't very hard, was it? So I hope you learned something. It's kind of interesting. It's really basic physics. It's the stuff they taught you in college level physics, but they never really explain why. It's all derivable. Again, hope you enjoy it. Sponsored by dspwidgets.com at www.dspwidgets.com. Thanks.